Welcome to this NPTEL course on Advanced Pre-stress concrete design. Last class we discussed about the shear and how to design for shear. In this part of the video, we are going to talk about torsion. So, we are going to focus on analysis and design of shear and torsion. We are in the module 5 and we have completed shear. Now, we will be moving on to torsion. What are the expected learning outcomes? The student should be able to understand what are the different types of torsion, what exactly torsion is, and then explain the failure modes of pre-stress concrete members due to torsion. Just like shear, how the pre-stress concrete member responds under torsion, we will be studying that. And one should be able to understand the effect of pre-stressing compared to reinforced concrete member. If you put pre-stress, how the torsional behavior is going to change, that is also we are going to talk about, and explain the effect of combined action of torsion, shear and flexion. So, how we take into account when you have multiple actions are acting in a cross section and how do we design for it. So, that is what finally we will have a design example and the student should be able to understand how to design a pre-stress concrete section for combined action of torsion, shear and flexion. Right. So, torsional moment, typically we call torque as an externally applied force, right. So, whenever a moment is acting about the longitudinal axis of the member, like what you see here, then it is called as a twisting moment or a torque or a torsional moment. Typically, torque refers to externally applied and twisting moment is internal force or moment. Okay. So, that is the typical nomenclature that we usually follow. Now, how the shear stress distribution is going to look like in a typical cross section is, if you see here, you will have this kind of shear stress distribution. Typically, in the corner to satisfy the stress equilibrium, and you will have 0 shear stress. But however, if you look at the middle location of the side, then you will have maximum shear stress. But in general, in torsion, the outer periphery will have more shear stresses and inner locations will have lesser shear stress. You can see that here at this location the shear stress is 0. Now, again the stress distribution also depends upon the shape of the cross section, whether it is a prismatic or non-prismatic, whether it is circular or rectilinear sections will determine the shear stress distribution that we will study in later part. Okay, what are the different types of torsion that we have? For example, some of the examples have been given here. We have typically 2 types of torsion. One is an equilibrium torsion, where torsion is induced by an eccentric loading. For example, you see here I have a beam with a projection, a cantilever beam with a projection. If you see, there is a load that is P that is acting at a distance of some eccentricity E. So, if I am looking at only the free body diagram of this longitudinal element, now you can see that if I transfer the force to this longitudinal beam, you will have not only P, but in addition to that I am also going to have a torsional moment which is equal to P into E. So, this is what we are saying. Whenever there is for example, there is an eccentric loading with respect to the shear center of cross section. For example, if you take the prismatic section, so you have shear center here. So, you see here the load is applied like this, certain distance, certain eccentricity. So, you are going to have torsional moment that is acting in the cross section, right. So, now the distribution of your torsional or twisting moment you can find out only using equilibrium conditions. So, that type of torsion is called equilibrium torsion, right. So, one more example is, this is a canopy slab, you can see a cantilever roof shell Now, all the load that it is there, right, let us say even self weight or whatever the live load that we are considering. So, all these things, if I look at it, how that slab is going to transfer the load to this beam, that will be always at an eccentricity. If you convert them into an equivalent load, that will be at a distance of eccentricity with respect to the shear center of the beam cross section. So, it will be basically twisting the beam. So, the beam will be subjected to torsion. Now, what are the distribution of a torsion on this beam? So, I can just using equilibrium conditions, I will be able to find out what is the torsional moment distribution on the beam. There one more example, this is for a precast system. Now, let us say this is a inverted, let us say T beam that you have, right. So, if let us say if this load that A is greater than B, then you will find that the overall Cg of the force is going to be at a distance eccentricity E from the shear center. That will also induce this torsion in addition to shear and bending on this inverted ledger beam. So, these are all some of the examples for equilibrium torsion. Again, equilibrium torsion comes. So, equilibrium torsion comes because of the eccentricity of the applied force with respect to the shear center on the cross section, and equilibrium conditions alone is sufficient to find out the twisting moments. Now, there is one more type of torsion that we have, which is called compatibility torsion. As you can see, this is very easily can be explained from this. Typically, these are your primary girders, and the one that is running perpendicular are called as secondary beams. Right. So, the primary girders typically run along the column line, and secondary beams are provided in the perpendicular direction to the primary girders, basically to reduce the span of the slab. And typically, we add secondary beams to reduce the span of the slab, so that we can reduce the thickness of the slab. And you know that in a typical building, the self weight of the slab is a major load contributor. If I can somehow reduce the thickness of the slab, then we can come up with a more economical design. So, that is the reason typically secondary beams are produced. Now, if you look at just the free body diagram of one example that you see here, if let us say that the primary girder, for example, let us say this is primary girder, and as let me say that the far ends are fixed for. Now, the AB you can assume this as a secondary beam, right. So, for the load that is P that is applied on the secondary beam AB, if we just take the free body diagram, now this joint A is connected with the beam CD. So, at this joint I am going to have a flexural moment. Let us assume that that is a rigid joint, right. So, that is going to develop a moment, flexural moment, because the beam is going to rotate like this, right. Along with this, this is also going to rotate, right. So, this rotation is going to be there. So, whatever the rotation that we have, flexural rotation, let us say theta A, that will be basically will become like a twisting for the beam that is CD, right. So, now I can design this connection of point A, the joint A, the way depending upon how much I want to transfer the torsion, I can design the connection. So, but this twisting moment, which is let us say this T is equal to MA, will develop only if this joint is rigid. If I make this joint A as a pin joint, which is going to allow rotation, then if it is pinned, then you will find that the MA will become 0, right, or let us say small up to cracking torque it will develop, and then it will become, it will lose its stiffness, and then. So, depending upon how you make the joint, whether it is rigid or thinned, and depending upon the detailing that we provide in the joint, now I can transfer the amount of twisting moment if I want to. So, that is what the saying. So, the compatibility torsion develops because the need for the member to undergo an angle of twist to maintain the deformation compatibilities, right. So, if this beam is going to rigid joint, if this beam is going to rotate in flexure, that will become the twisting for the beam CD. and the resulting twisting moment that is going to come on this primary girder will depend upon the torsional stiffness of its member, right. So, it is function of how, depending upon how stiff it is, that torsional moment or twisting moment will be generated. For example, you see here this T will be transferred to one end TAC and TAD like this, right. So, that how much it is going to develop based upon the relative stiffnesses of the members that are connecting at that particular joint. Now, that is what the code says, clause 41.1 if you look at it, where torsion can be eliminated by releasing redundant restraints, no specific design for torsion is necessary. Okay. So, that means what does it mean? If I am designing this as a pin joint, then the torsion will not get transferred to this primary girder CD, right. But when we do the analysis also, we have to explicitly create a hinge and make sure that the torsion stiffnesses are neglected in your analysis. So, when you do your STAD analysis or ETAPS analysis, you have to go and put torsional stiffness parameters as either very low value or equal to 0. So, then only you will not have any internal forces, that is twisting moment, that will be developed at the joint. So, if your torsion stiffness, if you keep it, obviously it will transfer the force to maintain the compatibility, and depending upon the stiffness that you have, you will develop some twisting moment. But it is up to the, typically what we do is, it is a good practice for secondary beams to be modeled like a hinge. So, typically engineers, design engineers, they model it like a hinge. So, they will define a flexural hinge at the connection of the secondary beam to the primary girder. So, it will transfer only shear, it will not transfer moment. Okay. So, depending upon what kind of connection that I want to do, so the code gives you the flexibility. So, but the detailing has to be done so that you are going to not have excessive crack widths. So, that is why the code is also going to mandate some minimum amount of transverse reinforcement should be there in those joints, so that even after cracking, even if rotation is allowed, but the crack widths under service conditions not going to be very high. Okay, now let us look at the other examples from bridges point of view. You see here, this is an integral bridge and it is a curved bridge. You see the bridge deck is directly connected to the long column that you have. So, if you take this bridge, right, if you take these columns, all of them are integrally connected to the bridge deck, and when you have an earthquake, let us say this bridge is in a seismically sensitive zone. So, when you have this kind of, let us say, longitudinal earthquake motions, or it is being subjected to, and typically your lateral inertial forces will be concentrated at the center of mass. So, if you have eccentricity between your center of rigidity and center of mass, then the deck will actually rotate like this. Okay. So, if there is an eccentricity, if center of mass and center of rigidity is coinciding, then there is no problem. But you see this kind of a curved bridge, it is not possible to have center of mass and center of rigidity coinciding. So, always you will have some eccentricity. So, because of that, the deck will undergo rotation. So, when the deck is undergoing rotation, then the columns will also be subjected to torsional moment. There is one more example we can see from the example of a skewed bridge. Okay. So, now during an earthquake motion, what can happen is the deck can actually collide like this, okay, and create these forces, okay, on the abutment. Now, depending upon the type of bearings that you have and depending upon the skewness of the bridge that you have, okay, and you will have, there will be an eccentric force that will be developed with respect to the center of rigidity of the column bend. So, you see here this is a 2 column bend, and typically the superstructures will be isolated from the substructure by some form of bearing, but however, the bearings will depending upon type of bearings that you have. If you have everything elastomeric bearing, then the forces will not get transferred, but typically we will be arresting some longitudinal movement at every joint to maintain stability. So, if you do have that, and if you have lot of friction that is developed, then this kind of force will get transferred. So, then your bridge bend will be subjected to torsion because of this eccentricity of the force. So, due to the collision of the skewed bridge deck with abutment during an earthquake motion, the bridge columns in a multi-column bend can be subjected to significant torsional moment based on the type of bearings that you have. Okay. So, you tend to have this kind of torsion as well. Now, there is one more case is a torsion in an outrigger bend of a bridge, again in the same way. Now, the outrigger bend is, let us say you have a portal, the portal is actually it is away from the, or I should say it is outside the bridge deck. So, in such a case, for example, if you see the bridge bent, the pier cap, again when you have an earthquake motion like this. So, what will happen is you will develop some torsional moment in this the pier caps, so of the portal. So, then you have to be careful. So, these are the conditions and examples in bridges the torsional moment can develop.